I'm going to be talking about an evolutive equilibrium code called FREEGSNKE that we developed within a collaboration between the UK Atomic Energy Authority and the Hartree Centre, which is part of the Science and Technologies Facilities Council in the UK. So first of all, what is FREEGSNKE and what can it do for you? What can you use it for? So FREEGSNKE is an equilibrium code, both static and evolutive equilibrium code for TOKAMAK plasmas. It's a 2D axisymmetric equilibrium code. It's a finite difference code, and it's a fully Python code. So FREEGSNKE stands for FreeGS, or Free Boundary Grad-Shafranov Newton-Krylov evolutive. And it's a code that builds on a previous open source Python code that was introduced originally by Ben Dodson called FreeGS, that I'm sure many of you will have actually heard of and probably used in the past. It has now a quite active community. We use most of the object-oriented infrastructure of FreeGS. For those of you who are familiar with them, we use the machine object, the equilibrium object, the profile object, and so on. But we've essentially replaced all of the solvers that are inside FreeGS. So in particular, we have introduced a new static free boundary Grad-Shafranov solver that is based on Picard iteration, that is based on Newton-Krylov method instead of the Picard iteration that are originally there in FreeGS. And then we've introduced a completely new capability, which is the one to do evolutive simulations of the plasma equilibrium. And FREEGSNKE can do both linearized dynamics and fully nonlinear dynamics. So now, before I go into any sort of detail on how these tools work and how you can use them, I sort of feel I need to address the question of why FREEGSNKE, why another equilibrium solver in a way. And this is probably a perfectly fair question given how many equilibrium solvers there are available out there. Well, originally, the truth is that we didn't, the collaboration I worked in, we didn't really set out to produce, to generate, to build and develop another equilibrium solver. Actually, FREEGSNKE was sort of a side product that became the main enabler of the collaboration itself. What we wanted to do was actually to use AI and machine learning approaches to plasma shape control. And we soon realized that we needed to develop an equilibrium solver to facilitate that. So we set out to build an equilibrium solver that would be friendly to AI and machine learning approaches. And this is basically why the choice of Python, and that is, I'm sure you know, most of AI and machine learning libraries are Python libraries. And so FREEGSNKE, being a Python code, can seamlessly integrate with those. In particular, we wanted to do reinforcement learning studies too. And so that's something that comes with reinforcement learning. You'll have to call your evolutive solver thousands and thousands of times from your machine learning libraries. And so FREEGSNKE eliminates entirely the need and the challenge that comes, the problems that possibly can come with those cross-language binders or socket interfaces that you need to have different kinds of codes talk together. Something that we targeted also quite explicitly was to have a stateful code. So we wanted a code that we can always use to restart a simulation from a point in a previous simulations where the system can be easily tracked and updated. And we wanted a code that would be stable enough for HPC deployment. And that is, of course, the case when you want to do when you want to train reinforcement learning agents, but also if you just want to build large libraries of equilibria to do surrogate model training, then you need something that is reliable enough to go on HPC and doesn't need a lot of human babysitting in a way. So what's in there in FREEGSNKE? What can you use it for? So first of all, FREEGSNKE is a static Grad-Shafranov solver So you can use it to build plasma equilibria, to calculate shape targets, shape matrices, virtual circuits, and so on. FREEGSNKE can both do inverse Grad-Shafranov static solves. These are the solves where you fix a set of magnetic constraints and infer the coil currents and the plasma equilibrium that can realize those, but can also do forward Grad-Shafranov solves, which is when you actually fix the coil currents and you want to calculate the plasma equilibrium that comes from them. And the reason I'm stressing this is that several of the use cases that I've already mentioned, from calculating the virtual circuits, for example, but especially when you want to calculate large libraries of equilibriums, or you want to use your static solver to then develop the evolutive solver, you need the forward Grad-Shafranov solve capability. And so this is essentially the main reason why we had to replace the original static solver that is there in FreeGS, in the original version of FreeGS. So FreeGS does have a static solve, but this is based on Picard iterations, and this is okay when you want to apply it to inverse Grad-Shafranov solves, but I'm sure if you've tried for forward Grad-Shafranov solves, Picard iterations are very often, especially for elongated plasma, numerically unstable. They will just not converge. And so this, in a way, wasn't enough for the use cases that we were aiming for. Of course, there's different ways we could have gone there. We could have just stabilized the Picard iterations, but we actually took inspiration from previous work at EPFL by Francesco Carpanese, actually, and we just implemented our own Newton-Krylov solver in FREEGSNKE, and this basically resolves entirely the convergence problem, the instability problems of the Picard iterations. So the static solver itself has now been extensively validated, and we use it on operations on MASU now. If you're specifically interested on the validation work, there's a paper out there by Cameron Pentland. We basically used FREEGSNKE side by side with the two main equilibrium codes that we use at UKEA. These are EFIT++ for equilibrium reconstructions of must upgrade equilibria in must shots, and Fiesta, which is another equilibrium code that we use quite a lot, that is a stabilized Picard solver. This, I'm not sure that you can see my pointer, but this is just an example of the kind of validation work that we did. This is basically a sequence of equilibria in a must-use shot that essentially we solved in FREEGSNKE and Fiesta based on parameters reconstructed by EFIT++, and then just compare to make sure that everything works as it should. One thing that I'd like to highlight is that even though FREEGSNKE is not nearly fast enough to enable real-time operation, it's still a lot faster than Fiesta, which, as I mentioned, is a stabilized Picard solver, and that is just because of the additional computational expense that goes into stabilizing the Picard iteration, and basically gives credit to the Newton-Krylov method itself. Now, of course, the main new capability with respect to FreeGS that FREEGSNKE introduced is the evolutive equilibrium solver capability. Basically, the dynamic solve allows the user to test how the plasma responds to control actions that come in the form of active voltages applied to the poloidal field coils by the power supplies. And so essentially you can use the evolutive solver in FREEGSNKE to do vertical stability analysis and control design for both vertical control and shape control and control validation for these, of course. So How this works is that basically FREEGSNKE evolves the state of the system between times t and times t plus delta t. The state of the system in FREEGSNKE is described by all of the metal currents, and this includes both the currents in the poloidal field coils and the currents in all of the passive wall elements that compose your tokamak. And of course, there's the plasma equilibrium at times t. And provided the control action, that is the active coil voltages applied to the poloidal field coils, FREEGSNKE solves the nonlinear problems that defines the time, the state at times t plus delta t with all of the new metal currents and new plasma equilibrium. So one thing that I need to stress here is that FREEGSNKE is not a transport solver and does not currently evolve the diffusion equation. So together with the control action itself, FREEGSNKE actually needs a prescription for the profile coefficients for the pressure profile, for example, at time t plus delta t. So these needs to be prescribed by the user and are not currently, at least, evolved in a self-consistent way within the code. So how does this work? Well, basically, FREEGSNKE couples the currents in the metal, both active poloidal field coils and passive structures, with the plasma. And of course, there's a number of ways to do this. Again, we take inspiration from work at EPFL, and for the plasma, we essentially describe the evolution through a one-dimensional equation that is practically a simplified version of the Poynting theorem, or basically the circuit equation in each of the domain points in the plasma, which are contracted by the current distribution, the normalized current distribution of the plasma itself. And then, of course, these are all coupled with the Grad-Shafranov equation to describe the equilibrium. We solve this from a numerical point of view. We solve this again with the Newton-Krylov method, but we have sort of our own recipe to do this. It's a slight modification rather than applying the Newton-Krylov method to the problem, to the full problem as it is. We essentially have a staggered strategy in which we advanced with the Newton-Krylov method the solution on two independent formulations of the evolutive problem. One that is based on the currents, on the metal currents, and one that is based on the plasma flux. And we find that this improves the convergence properties and makes everything a little bit faster, in particular with respect to collinearity and stagnation issues that can happen when using Newton-Krylov methods. We've done, of course, our validation exercise on these capabilities too. Those are related to the evolutive capabilities. So this is just an example of the validation of the vertical growth rates that come from FREEGSNKE against RZIP, and of course, well, the vertical growth rates that you can derive using FREEGSNKE are deformable growth rates. So they do take into account the deformation during the movement of the plasma, while the RZIP values, of course, come from a rigid model. So essentially, this validation was designed on equilibria where the deformations are minimized during displacement. And we have quite recently started to use FREEGSNKE actually on pulse design as a flight simulator, essentially, from MAS2 for MAS2 at UKEA. And this, of course, serves also as a validation of the code itself. This is just an example of basically a simulation that recreates the flat-off phase of a MAS2 shot. And that is based on using the active voltages applied to the PF coils as recorded in the experiments, together with the profile coefficients and properties as reconstructed by the EVIT reconstruction, and then just solving the evolutive problem, basically simulating the entire shot from an initial condition that is also an if-it reconstruction. And as you can see here, what I'm showing is essentially the FREEGSNKE simulation on the left compared to the sequence of if-it reconstructions to the right, and just a few panels that show the evolution of the standard shape targets and are used for shape control as reconstructed by if-it and as basically realized in the FREEGSNKE simulation. Now, this is probably redundant, but yeah, the reason I'm presenting here is that this FREEGSNKE, this code is now open source, is available on GitHub, and we really hope that this is going to be useful and there's going to be good community engagement also in developing further the code itself. We put effort to try and make this as easy as possible to adopt to new users. It's, for example, FREEGSNKE is on PyPI, so it's very easy to install it. And we try to be as diligent as possible. Of course, there's always room for improvement, but we have systematic and coordinated code documentation in place, and we have the docs for the entire code and an automatic CI pipeline. Something I want to spend a minute specifically on is basically the series of examples or tutorials that we have available. This is going to grow functionality. We try to design an example that basically shows how to use it and possibly where the limits are. We have an example on how to set up a new TOKAMAK machine. All of the plots that I've shown you so far are based on MASTU, and that is just because we use FREEGSNKE mostly on MASTU, but we have an example based on an ITER-like machine, a Spark-like machine, and so on. We have an example on how to set up magnetic probes, but also on slightly more advanced capabilities. So, for example, how to design, how to build and calculate virtual circuits and how to apply them to an equilibrium. And of course, we have an example on how to use the evolutive solver, and for example, here showing the differences and the limits in the between, for example, using a linear evolution with a fixed linearization with respect to actually solving the full nonlinear problem. That shows quite well how different the two are when you're evolving the plasma in a vertical displacement event where the equilibrium evolves substantially. There's